Grid is a fascinating piece of engineering work, I would say, but needs to accommodate these rapid changes in the technology and also be used as a vehicle of significant decarbonization of the way how we actually affect the environment around us to make sure that we keep this environment for as long as we can in a livable conditions.
Hi everyone, I'm Barbara Humpton, CEO of Siemens USA, and thanks for joining me for the Optimistic Outlook. One of the things I'm really optimistic about is the ability of technology to help us tackle problems related to the environment and renewable power for the future. In an earlier episode 5, we had Vic Shao of Amply, and we talked a little bit about the economic models that would help us overcome barriers to adoption for electric vehicle charging. But you know what? Economic models aren't the only hurdles we have if we really want to build the renewable grid of the future. And that's why I'm delighted to have today's guest on the podcast. In this episode, you'll hear from Dr. Sonja Glavaski. She's the chief scientist for Energy Digitalization in the Energy and Environmental Directorate at Pacific Northwest National Laboratory. That's part of the U.S. Department of Energy National Lab ecosystem. Sonja's had a remarkable career. Join me now as we learn from her. Sonja, welcome to the podcast.
Thank you, Barbara.
It's such an interesting thing to think about your background. You have such an ability to take theoretical concepts and actually carry them all the way through to practical implementation. I assume it's a background in systems engineering that supports that, and your experience with research and the application of technology to take concepts into the control room. Tell us about your background and how did you arrive in your current position?
It is really interesting how I ended up where I ended up because I always loved math. But then I also want to see, as you pointed out, see things that I actually work on make everyday lives of common person better and more interesting. And I figured out very early that engineering is the way to go. So my original training is in electrical engineering, but with a focus on control system, which is very mathematical discipline. And as a part of training, you actually learn how to put systems together. So that's how I ended up being somebody who's actually very, very much interested and has had a chance to also work in areas that allow you to work on these different large-scale system integration. So I spent 15 years in different industry R&D organizations. And that's where I got exposed to various aspects of energy sector. And I got really passionate about decarbonization of the energy production, consumption, energy efficiency. And I decided to join US government and spent 5 years as an RPE program director. And now I am with Pacific Northwest National Lab.
Fantastic. One of the things that I like to talk to my team about is the fact that when the National Academy of Engineers put their minds to ranking the top technical innovations of the 20th century, the top was not space travel or even the internet, it was the electric grid. And it seems like now here in the 21st century, we're relying even more on the electric grid. It's not only the source of our power, but it's also a tool we have for decarbonization. How do you view the transition and the work of the grid at this moment in time?
Grid is a fascinating piece of engineering work, I would say. But it evolves as, our technologies and knowledge about different areas that have to do with energy production and consumption and coordination management evolve as well. And we are really living in the interesting times when we are experiencing a paradigm shift in a very short amount of time. And we have to deal with a huge system that works perfectly fine, but needs to accommodate these rapid changes in the technology and also be used as a vehicle of significant decarbonization of the way how we actually affect the environment around us to make sure that we keep this environment for as long as we can in a livable conditions.
You know, I've heard a lot of people talking about the challenges for decarbonization ahead, and we've actually had another episode about the economic models that'll help, and surely there are regulatory issues to be handled as well. But you recognize there are technical difficulties as well. Tell us about the major technical challenges you're working on.
What is the major technical challenge is how to actually bring all these little pieces together, and how do you manage them in synchrony. So there is a wide perception that actually we have technology, we just have to connect it to a grid. But given the way how we manage the grid and how we actually guarantee its reliability and resiliency does require lots of new technologies that will be able to allow us to do that. And technical challenges are going from the way of understanding dynamics of the grid, such a large system, because we are dealing with variable renewable power resources. We are at the same time dealing with the very different usage patterns, for example, by presence of EVs and different kinds of more electrified buildings that we will be seeing in the future. And then the question is, how do you actually make these technologies maximally efficient, minimize the emissions, but at the same time make them economically viable? And I don't disagree that economics and regulatory challenges are major challenges, but they have to be actually addressed hand in hand with technical challenges. And throughout my career in this field, I have seen that actually regulatory and policy people do reach out to technical experts to shape the way how these policies are being actually established, and also how do we build in certain aspects of these new technologies, such as more variability, shared risk, enhanced resiliency into economic vehicles as well, which may result in the ways how we will change markets or how we will actually modify the standards of who can connect to grid or not connect to grid.
So in essence, when you're working on the art of the possible, that's also then enabling certain changes in those economic models and demands different regulation.
Absolutely, especially with the rise of some of the digital technologies that allow us to communicate and exchange information fast, to collect information as well fast and process it. So we could react very, very quickly, and we can not only control and optimize performance of devices, but we can also affect the whole system, and that will result in the different outcomes in the markets. Because markets in this space are not your traditional economic markets. They're a mix of economics and engineering, because you cannot push power through a grid without being able to respect physical limitations. And that has to be taken into account when you are actually dealing with the different economic transactions. So it's very, very, very intertwined and very interdependent. So that is something that actually distinguishes grid as well. So some people may not say it is a technical challenge, but it is.
Well, it is. And I think as I've studied your work a bit, you do share with audiences who aren't familiar with the topic the idea that power distribution used to be one way, top down. And now you talk about the edge and what's happening at the edge. Explain so that those who aren't familiar with it can get it.
So our grid was put together in early 20th century when we had large power plants that were producing power, and grid was built with the one purpose: to deliver this power to the end consumer. And it's managed top down, very one directional. However, with the technologies that allow us to have local power production, such as solar panels, for example, or store the power, such as in the storage, we have now situations where we actually are producing more power than we need to consume locally, so we can perhaps share it. And we have to figure out how to do that in most effective way in terms of making all these assets as efficient as we can. So if you produce this power, try to use as much of it as you can. And then also, how do you manage? So paradigm of management is very, very different. And traditionally, we would separate what is called transmission, which is high voltage part of a power grid, from the lower voltage, which is distribution. And we have made lots of investments in a transmission, and we can do two-way power distribution at that level. However, on the distribution side, most of the networks in the United States especially are radial, which means that you have literally a cable that brings power from some station to the consumers. So if you produce extra power, you cannot return it. So we're developing technologies that will allow us to be able to do that, but do it also in a safe and reliable manner, because there are laws of physics that you have to obey to make sure that everything works in synchrony in the grid.
Those pesky laws of physics. You've been living in the same world that Siemens operates in. What we've been working on is that nexus of the physical and the virtual worlds, bringing digital tools to really be part of this large physical infrastructure world we've been creating all these years. And yes, it's a shame when the laws of physics get in the way. But we have been creating islanded grids, microgrids for some of our customers, and it's been really helpful. Some people have criticized saying, hey, creating microgrids is actually taking people off the grid. We've been thinking of it as a way to integrate with the grid. How do you view it?
I actually view it probably closer to Siemens's view, because as we all know, microgrids started initially on a defense side of the technology to provide power where we didn't have really a local production. And then on a more commercial side, we are looking into ways how to actually enhance resiliency. For example, in the case of some unforeseen events, how can you guarantee for some critical loads that you will have power? And that's where microgrids came to be. However, I believe that as we develop some of these technologies, that the microgrids are going to be slightly different. They will be part of a grid, and they will not necessarily have the old-fashioned one point of contact with the grid, but will be basically by use of, for example, smart switches, relays, control technologies, we can actually carve out a portion of a distribution and assure that we do provide power, but then we can also seamlessly integrate into a grid. So if you think of similar system as an internet, none of us really think about underlying architecture of the network. So I hope that pretty soon we end up with a power grid that looks like that, where we can actually develop these, I call them clusters and microgrids that do provide power locally, but if needed can be actually shared by the neighboring portions of the network, or maybe even put power back into grid.
Oh, I'm looking forward to seeing that progress. But one of the things I keep hearing as one of the technical challenges is storage. Where do you see the maturity of storage as part of the solution?
Well, we're going back to laws of physics and chemistry in this case as well. So we cannot deal with variable power and variable demand patterns without storage. We can, up to a certain extent, use flexible loads that provide similar functionalities as storage, but storage by itself is still necessary. And most of the storage that we are deploying is electrochemical. And the issue is there that you can store only so much power, and then also there are limitations in the rate of charge and discharge. So storage is very critical, but we still need to work on lowering the price, because economics comes into play. It can be pretty expensive. Some other sectors are working on storage for different purposes. So I think that EVs and electrification of transportation can push some of these constraints that we see in the electrical storage and that we were not necessarily tackling when it comes to the grid. But then there are also other types of energy storage. You have flow batteries that are being developed, stationary large storage. There is thermal storage. So these are all things that we need to think about how to use them all when it makes sense and when physical parameters of the storage actually are benefiting the grid.
We've had an episode about the economics, as I say, of the EV ecosystem. We've had an episode on 5G. I'm delighted to be talking to you today. I'm thinking maybe storage is one of those things that's worth taking an optimistic look at. But another one I know you're deeply engaged in now is artificial intelligence and machine learning. Tell me what you and your team are doing on the digitalization front.
So in the national labs, we are looking into ways how to use new advancements in artificial intelligence and machine learning, and to perhaps develop them further for the applications that are of interest to U.S. Department of Energy and the energy sector. Because some of these technologies have been developed by different purposes, primarily for what I would call data analytics, or creating something that would mimic human beings. What we would like to do in this sector is actually leverage some of the technologies that you mentioned, fast computation platforms, 5G computation, then try to be able to actually turn all this data into actionable information. And that's where most of the work, I would say is going. So what we are really focused on right now in PNNL is developing some of the technologies that will be enhancing and accelerating some of the approaches that we use in management of a grid, monitoring, cybersecurity. But we are also slowly but surely moving into human-machine teaming and trying to figure out how we can actually enhance some of the operations of these energy systems, specifically grid. Because for example, in the autonomous cars, a Society of Automotive Engineers developed different levels of automation for the cars, and the whole industry goes by that. So some of the companies claim that they are at the level 4, which means that some functions could be performed by car itself without any kind of human supervision. Grid per se is what I would call safety critical system. We cannot let it be yet, or not for a near future. So we're trying to understand how to use some of artificial intelligence and machine learning approaches to actually help operators of the system process information in a more timely fashion, react fast, also get a better insight in the system. Sometimes just simple things as visualization help a lot, because we as human beings are very good at processing pictures, sometimes better than processing information in the form that you get just from the senses. So lots of exciting things. And also as a national lab, we have access to high performance computing platforms. So we do use artificial intelligence and machine learning for scientific discovery. So we are basically developing digital twins of different systems and trying to accelerate understanding of some of these systems, but also design, such as, for example, materials.
The digital twin of a network is it's a fascinating topic, because these are just highly complex interdependent systems. I'll tell you, Sonja, it's been interesting to think about what you've seen develop over your career. I'd love to hear from you. What are some of the most important developments you've witnessed during your career, and what do you think is the biggest thing that's likely to happen in the next decade?
Well, I've been really engaged in energy, I would say, for the last 10 years. And initially, things were moving slowly. And I think some of the development in renewables generation that drove price of the energy down accelerated adoption of these technologies and deployment. So this is something that affects a lot how system is evolving. On top of that, there is our desire to actually decarbonize this sector, because big portion of emissions in energy sector are coming from power production. And we are switching the mix of the power generation. So what is really exciting is also to see how awareness among the average consumer is rising, and is actually consumers are the ones who are asking. States in the United States are the ones who are having renewable portfolio standards. And then people who operate grids such as utilities or RTOs and ISOs they of course have to be responsive to their consumers. And that's what is fascinating, how this human need to actually do good is driving the evolution of the technology. And what I think yet has to be done, and I can see glimpses that people are recognizing that this integration of the system by means of digital technology, where you actually go through more automated, more autonomous devices that could actually perform functions that are built into them, and you don't have to have too much of a human supervision. And then the other big wave is electrification of transportation. So first wave was renewables generation. Now it's electrification of transportation, and that's something that we yet have to figure out how to do.
That actually is fascinating. So as one of the things I love to do for our audience is to paint that picture of what the future looks like when these things you're envisioning are in fact accessible and successful. What kind of life will we be able to enjoy? How will it impact our societies?
Well, I think that ideally we would see electrification, lots of sectors. People are talking about electrification of the buildings, appliances. So we'll probably see a world where more DC power is actually being used locally, and more renewables, more storage, very automated system, and very flexible. So you can have a plug and play features where you can actually add things and not have to deal with lots of restrictions. And then also electrification of everything, including air. I'm actually big on aircraft electrification. So I have done some things there, and that's where storage needs to help. So this will be very impactful, but will completely change. We'll have more travel on demand, more short route travel, and then how does that interconnect with the grid, and how we enhance the system to actually be able to serve all this will be a challenge, but a good challenge, because the outcome will change the way how we live. And I think that we will go back to much cleaner environment, much cleaner air. People may do more things locally. We will still be connected globally, but that will be due through communications and virtual means.
So all of this is within reach with the technology that's emerging today, and I thank you for your contribution to bringing this all to our futures. Thank you so much, Sonja.
You're welcome, and thank you for inviting me to your podcast. It was a pleasure.
Please follow us on social media and on your favorite podcasting platform. Thank you for tuning in.